In the previous clips, we've seen how precipitations develop and how they are distributed over the Earth. Now, it is time to look at what happens to the rain falling on the ground. Where does it go? How does it reach the sea? In summary, we want to look at the water cycle. The knowledge developed here will also be of great importance for Module 6 of this MOOC. To look at the water cycle, we can start from the sea, where water evaporates and is taken over by the overlying air masses. Driven by the low pressure dominating in warm conditions, the air will rise and will be carried by winds towards the continents. By cooling, the air mass will become saturated in water and rain will fall. Precipitations can either go along the ground, in which case one talks of runoff, or can infiltrate into the ground. Following different paths, all waters will eventually reach rivers and the sea. In this model, we only look at the subaerial path. We will focus on the underground one in the Module 6, the hydrogeology module. Water falling in areas of low elevation and covered with vegetation will only move slowly, will interact with rocks and contribute to the formation of soils, a key component for various organisms. Slowly but surely, waters will then reach and join creeks and rivers. In the other areas, for instance in the poorly vegetated mountainous regions, things will be faster and rougher. Here, valleys are narrow and steep and torrents will have a more tumultuous course. Waters will form first creeks, then larger torrents and rivers, getting out of the narrow mountain valleys, traversing the large plains, and eventually reaching the sea. During this journey, a number of things will change, from the slope and the vertical section of the valley and the amount of water flowing through it, eventually impacting the ability of the river to erode or, on the contrary, to deposit sediments. It is useful at this stage to introduce a few theoretical concepts. The carrying capacity is a measure of the amount of sediment transported by the river and of the grain size it can carry. Carrying capacity is primarily dependent on the velocity of the water flow. The equation shows how the flow velocity depends on the discharge and on the section of the channel it is flowing through. Imagine, for instance, that we have a sudden increase of water discharge. If the channel section cannot change significantly, this will result in a strong increase in velocity and therefore of carrying capacity. Let us briefly look at changes in velocity and channel sections along the river. A very important feature controlling the water velocity is the gradient of the river. Rivers in stable settings are steep close to the core source and become gentler asymptotically, reaching a horizontal level called base level. The most obvious base level is obviously the sea. The profile is generally stable, but if the base level is modified, for instance by tectonic uplift or sea level change, then the river will start eroding or depositing in order to go back as soon as possible to equilibrium. In general, the steeper the slope, the higher the flow velocity. From the source to the sea, valleys generally become wider, which implies that the speed decreases. In the same direction, however, rivers discharge increases because the affluent rivers join the main river. As long as the section remains constant, this results in a slight increase in velocity. A way to link the speed of water flow with erosion, transport, or sedimentation is the Houston diagram, in which the velocity of the flowing water is plotted against the grain size. Let us how to read the Houston plot. Imagine you have a river flowing at 5 centimeters per second. The corresponding line falls completely in the field of sedimentation, which means that the river will not be able to pick up any clasts, not even the small ones, and the river will not erode. Consider now a river flowing at 100 centimeters per second, represented by the green line. This river will be able to erode clasts larger than 5 millimeters, which might lie on the riverbed. On the contrary, the river will pick up all grains smaller than 5 millimeters and larger than 0.04 millimeters. Interestingly enough, finer grain clasts will not be removed from the river bottom because of the electric forces keeping these clay minerals together. If water flows at 800 centimeters per second, it will remove all grain sizes it finds on its way. Bedrock will be found on the river floor. The Houston diagram is also very useful to learn what happens when the speed of flow changes. Imagine that a river loaded with all possible grain sizes and flowing at 800 centimeters per second suddenly decreases its speed to 60 or 70 centimeters per second. Then it will dump most of the sediments and will only carry grain sizes smaller than 0.05 millimeters. Imagine, on the contrary, what happens during a large increase in water velocity, reaching, for instance, 700 centimeters per second. From the Houston diagram, you can see that the river becomes erosive. Precipitations are not always in the form of water, but can also take place as snow. When this goes on for a long time, this can eventually lead to glaciers. Glaciers are very powerful agents of erosion and transport. Under their own weight, glaciers move constantly down the valleys. The movement is slow, typically around 1 meter per day, but do not underestimate them. They can be very slow, but they can be very strong. Part of the downward movement is accommodated by gliding on the bedrock. Part of it is taken over by the solid state flow of ice. Descending towards lower altitudes, the glacier will reach warmer regions and ice will start melting. As a result, there will be a point where the downward movement of the glacier is compensated by melting. The glacier has reached a steady state, characterized by a stable position of the glacier front. This, however, does not mean that the entire glacier is inactive. The ice will keep on moving from the high to the low altitude, constantly carrying sediments scraped from the bottom and the sides of the valley to the front, like a conveyor belt. All these sediments are transported towards the tongue of the glacier, where it is deposited, forming moraines. At present, the size of the moraines is limited, but this has not always been the case, as we've seen when looking at climate change. During ice ages, huge glaciers eroded major valleys, presently, for instance, visible in the Alps and elsewhere, depositing huge amounts of sediments at the glacier front. A couple of modules ago, we've seen that as soon as mountains grow, erosion is activated. In general, the higher the relief, the stronger will be the effects of erosion. Erosion is the source of the terrestrial sediments. The type and amount of sediment eventually being delivered to the sedimentary bases onshore and offshore will depend in a significant way from the type and amount of sediments produced in the source area. How sediments are then produced? What will be their grain size and composition? What are controlling processes? These are the issues we want to address in this module. A very common form of erosion is physical or mechanic weathering, which implies that rocks and the mountains are crushed, resulting in smaller blocks. We can mention two important processes. A very powerful mechanism is thermal expansion. Daily temperature variation in the mountains can be very high, possibly up to 20 degrees. Rocks will expand and contract and consequently break. Rocks can also break because of the expansion associated with freezing of water percolating in cracks inside the rock. As you know, ice has a larger volume than water and causes then widespread fracturing. These processes in the mountains are very effective because rocks typically have widespread discontinuities caused by layering or tectonic fracturing. Fractured blocks will fall down. Walking along the foot of the mountains, you can see easily the results of intense mechanical weathering, huge masses of rocks. Interesting to observe that you will find the largest blocks at the bottom of the scree. Rocks can also be eroded by chemical processes essentially driven by water. Simple examples are oxidation of iron-rich rocks and the dissolution of carbonates. The latter can cause the formation of large caves and tunnels in the subsurface. These are called karst systems. A widespread phenomenon and one of great importance is erosion is the chemical weathering of minerals such as feldspars, which are very common. For instance, in granites, and various types of sandstones. The CO2 contained in the rainwater will react with the feldspars, creating clay minerals, typically rich in aluminium and various ions, such as potassium, which is then dissolved in water. Note that because feldspars and micas are weathered away, also the granite will fall apart, leaving quartz grains, clay minerals and ions, which are then transported away by waters. In the picture, you see the results of chemical weathering. Waters and rivers have no coarse grains. All is dissolved and brought in solution to the valleys. Very different from rivers where mechanic erosion is dominating. Weathering, very different processes leading to very different types of erosional products. In the plot, you see that temperatures and precipitations control the type of weathering occur in a specific region. Warm and wet domains are ideal for chemical reactions. Dry and cold mountains, on the contrary, will be dominated by mechanical erosion. When talking about climate change, we've seen that temperatures and precipitation have varied significantly during the history of the Earth. This suggests that also the type and amount of sediments produced in an area can also change because of climate. If, for instance, climate becomes warmer and wetter, a given region will cease producing coarse-grained sediments with various minerals and will start instead delivering sediments which are clay-rich and with little feldspars and micas. Indeed, very important modifications.